Parent functions. Many situations in the world have people study and collect data that is interpreted through graphs. They usually follow one of the 12 patterns we are about to learn. By recognizing these patterns, or what we call the parent functions, and using transformations, we can derive a function for any given data or data set to make predictions. Some people get paid a lot of money to do this. Each of the patterns will be explored deeper in subsequent units. For now, focus on the general shape of each parent function and some of their basic properties. The first 4 parent functions are the identity function, which is a linear function that goes directly through the origin, the quadratic function, which is y equals x squared, or the basic parabola. You have the absolute value function, which is y equals absolute value of x, and you have the square root function, which is y equals positive square root of x. The cubic function is another parent function that we have, as well as the reciprocal function. And we have exponential function, or y equals e to the x, and we have the natural log function, y equals natural log of x. We also have the sine function, or y equals sine of x, as well as the cosine function, or y equals cosine of x. We have the logistic function, and we have the greatest integer function. It's also known as the step function. The first parent function is the identity function. It's the parent function for lines that has a slope of 1 and a y-intercept at the origin. In other words, I of x is equal to 1 times x plus 0, where 1 is our slope, or our m, and 0 is our y-intercept, or our b value. When simplified, it's written as I of x is equal to x. The tables shown here to the left are random points of this function that are shown in the graph. So we have -3, -3, -2, -2, -1, -1, 0, 0, 1, 1, 2, 2, 3, 3. These are just random points that are found in this function. Both the domain and range of our identity function are all real numbers. If you wanted to write these in interval notation, they would be for the domain, x is contained in, and it would be the open bracket from -infinity to +infinity. And if you were to write the range, you would write that I of x, or y, if you had it written in terms of just x and y, is contained in the set from -infinity to +infinity with open parentheses on both sides. The squaring function, or the quadratic function, is s of x equals x squared. The domain consists of all real numbers, but then the range of this parent function only goes from 0 to infinity. And it does include 0, since the vertex of the parent quadratic or squaring function is 0, 0. For the absolute value function, we see that it looks like a V. Absolute value of x, you can write it sometimes in a calculator as ABS, and then open parenthesis, and then x in between the parentheses, or you can write it with the vertical slashes and x in the middle. The domain for the absolute value function is all real numbers, and similar to the quadratic or squaring function, the range is from 0 to infinity, including 0, since its vertex is 0, 0. For the square root function, its domain only goes from 0 to infinity, because it begins at the point 0, 0. And then the range for the positive square root function, and notice if there's no minus in front, or if there's no plus or minus in front, it's automatically assumed to be positive. So we're only taking the positive values of the square root of x in this case. And the range of this parent square root function is from 0 to infinity, and we include 0, since the square root of 0 is indeed 0. This parent function is called the cubing function, or sometimes called cubic for short. And whatever your x value is, you cube it to get your y value as your output, or your c of x function, and the domain is from negative infinity to infinity, or all real numbers, and the range is similar, from negative infinity to infinity, or all real numbers, mainly because when you do cube negative numbers, the output value is also negative. Here's a graph of the reciprocal function. When you have the reciprocal function, it is 1 over x, and because the denominator of a fraction cannot equal 0, when you substitute 0 in, it is undefined, or it has a vertical asymptote. And also, since the numerator's power, or exponent, is less than the denominator's exponent, we also have a horizontal asymptote at y equals 0. So that is why the domain consists of all real numbers excluding 0, and the range also, it contains all real numbers excluding 0. If you were writing these in bracket notation, you could write the domain as from negative infinity to 0, non-inclusive, in union with 0 to infinity. And you can do the same with the range. For the range of this function, you can write it as negative infinity to 0, not including 0, or non-inclusive, in union with 0 to infinity. It is important to note that this is the first parent function that does not pass directly through the origin, which is the point 0, 0. However, the function is still centered about the origin, because both of the asymptotes that the reciprocal function has intersect directly at the origin. The next parent function is the exponential function. It can be written as e raised to the x power, or as exp of x in some calculators. Notice that our function's y-intercept is the point 0, 1, since any number raised to the 0 power is equal to 1. This function has no limitations within its domain. Therefore, its domain is all real numbers. When written in interval notation, it would become x is contained in the set of real numbers from negative infinity to positive infinity. The range, however, does have limitations. As x continues to increase, the function continues to increase, making its upper bound positive infinity. However, as x decreases, the exponents become negative. And when this happens, we have e to the negative first power, which is equal to 1 divided by e. And e is about 2.718, so that's kind of close to a half. But then if you do e to the negative 2, it becomes a 1 over e squared. And when you have e to the negative third power, it becomes a 1 over e cubed. So this e value is becoming much bigger in the denominator, making it become closer and closer to 0. Since there is always a 1 in the numerator when you have negative exponents, this function never reaches 0. Therefore, the range for e to the x is from 0, not including 0, to positive infinity. The next parent function is the natural log function. And the natural log function, or natural log of x, is equivalent to the logarithm with the base of e of x. And the natural log of 0 is undefined. And if you take the natural log of 1, you get 0. Natural log of e is 1, and e squared is 2, and so on. The domain for this function is from 0 to infinity, not including 0. However, the range of the natural log of function is all real numbers. Because we have this vertical asymptote happening at the y-axis, it shoots the function straight down as you get closer and closer, as the x values get closer and closer to 0. So that is why the range is so large. The next two parent functions are the sine and cosine functions. And both of these trigonometric functions oscillate between -1 and +1 for our y values. and they are included because if, for example, you take the sine of negative pi over 2, you get negative 1 as your output. And similarly, if you take the sine of pi over 2, its value is positive 1. So because negative 1 and positive 1 are both included in the function values, the range for the sine of x is that the sine of x is contained in the set from negative 1 to positive 1, including both endpoints. And cosine of x is generally the same. It again oscillates between negative 1 and positive 1. And for example, the cosine of pi is negative 1, and the cosine of 0 is positive 1. So therefore, the negative 1 and positive 1 boundaries for the range are included with square brackets. And the domain for both of these is all real numbers. You can go as far left or as far right as you would like. You can also rewrite the domain as x is contained in the set of real numbers from negative infinity to positive infinity. And you can do the same for the domain in cosine of x. X is contained in the set of real numbers from negative infinity to infinity. The next parent function is the logistic function. L of x is equal to 1 over the quantity 1 plus e to the negative x. And the domain for the logistic function is all real numbers. However, as you can see within this graph, there is a range restriction, and it only goes from 0 to 1 in y values, not including 0 and 1. There are actually horizontal asymptotes that are occurring at 0 and at 1 for the y values. The last parent function that we're going to talk about is the greatest integer function. And you usually can write it as g of x equals int of x, or you can write it as g of x is equal to the greatest integer function with these extra brackets on either side. And what this does is when you evaluate the function from 0 to 1, when it's in between these values, it always goes back to the previous integer before it. You could think of it as truncating decimals or cutting off the decimal values that you have there, at least for positives. Because if you were to have 1.1, it would go to 1. 1.2 would go to 1. 1.7 would go back to 1. In negatives, you end up rounding down still to the previous integer value. For example, negative 1/10 is about here. It goes down to negative 1. And negative 9/10 is right here, and it still goes down to negative 1. So the domain for this greatest integer function is all real numbers. However, the range consists of all integer values, which is denoted by capital Z. Now let's look at some examples on how to find the domain and range from a function. To determine the domain and range from the equation of a function, imagine its graph first and see if that helps. For instance, any sloped line of the form L of x equals mx plus b, where m is not equal to 0, can easily be graphed on the xy plane, and determining its domain and range from the graph is fairly simple. So what is the domain of the line L of x, which is equal to mx plus b, if m cannot equal 0? Well, the domain, if we look at the graph that's shown here to the left, there are no restrictions on how far left or right we go. So the domain, you can write it as x is contained in the all real number set, or if you like the bracket notation, you could also write it as x is contained in the set of real numbers from negative infinity to positive infinity. Now we can answer the question, what's the range? If we look up and down along this graph, again, there are no restrictions. So the range will be L of x, because that's what it's referenced as in our graph, is contained in all real numbers. You could also write it as L of x is contained in the set of real numbers from negative infinity to positive infinity. And here's the solution, and it does match the solution that we had found. The x values are contained in the entire real number set, and the range is also contained in the all real number set. It is a good practice to imagine at first that the set of all real numbers, or the special R, is the domain of a function. Like with the graph, it will take practice to recognize domain restrictions from the formula or the general equation that is given to you. Stay tuned on how to do that. Let's look at another example. What is the domain of the parabola capital F of x, which is equal to x squared? And then what is its range? Well, let's first try to imagine this graph. If we have the xy coordinate plane, our parabola starts at the origin and goes upright on both sides, kind of making a U shape. So the domain, if we analyze it from left to right, there are no restrictions on the domain. So the domain can be written as x is contained in the set of real numbers between negative infinity to positive infinity. Or you could also write it as x is contained in the all real number set with no restrictions. And now what is the range? Well, the range does have a restriction. It goes down and approaches the origin. It does have the ordered pair 0, 0, and then it goes up. So the range, and we have it written as f of x, capital F of x, it's contained in the set of real numbers from 0, including 0, to infinity. And here's the solution for the domain and range for our parabola f of x equals x squared, and it does match up with what we found. X is contained in the entire real number set, and f of x is contained in the real number set from 0 to infinity, including our endpoint of 0, because it does cross both the x and y axis at the origin. Here's another example or exercise that we are going to complete. It asks, what is the domain of our function capital A of x, which is equal to the absolute value of x, and what is its range? Well, if we think about and draw our absolute value function, let's start off there. We know that the absolute value function starts off at the origin, and as x increases, our y increases just like a line, because the absolute value of 1 is 1, absolute value of 2 is 2, absolute value of 3 is 3, and so on. But now if we go in the negative direction, well, the absolute value of negative 1 is positive 1, absolute value of negative 2 is positive 2, so it's going to rise again from right to left. It looks like a V. So now the domain, now if we analyze both the left and right, there are no restrictions in the domain. So you can write the domain as x is contained in the entire real number set, or you could also write it as x is contained in the set from negative infinity to positive infinity. And now what is the range? This one does have a restriction. We're starting off at 0 and we're going up towards positive infinity. So the range, and we're using a of x for our function that is contained in the set. We are including 0 because, again, at the origin, it has a defined value. The x value is 0, it is 0. So 0 is included, and it has no restriction as to how high it goes, so it goes up to positive infinity. And here are the solutions. We did find that the domain is the set of real numbers, and the range for our function a of x, it's contained in the set of real numbers from 0, including 0, all the way up to infinity. And the graph of the function, whichever one you're being asked a question of, really helps to paint the picture for the domain and range. One of my teachers, either in high school or college, always had a saying when it came to analyzing functions: when in doubt, graph it out.